This cosmic cloud is a beautiful lie. The Crab Nebula, the glittering remnant of a star seen exploding in the year 1054, is not just a distant spectacle 6,500 light-years away. It is a cosmic laboratory where the laws of physics are stretched and broken on a daily basis. By the end of this journey, you will know 25 of its deepest secrets, each one stranger than the last. We will see a dead star that spins 30 times a second, sudden flares of energy that defy explanation, and structures moving at half the speed of light. What do you think is the most unsettling part of a universe that refuses to follow its own rules? At its very core lies a heart that refuses to die. The first of our 25 strange phenomena is the engine of the entire nebula, a pulsar officially known as PSRB 0531+21. This is the collapsed core of the star that exploded a millennium ago, a city-sized sphere of pure neutronium so dense that a single teaspoon of its material would weigh as much as a mountain. And it is spinning, not lazily like a planet, but with a frantic, terrifying energy. It completes a full rotation 30 times every single second. Imagine a sphere the mass of our sun, but compressed into the width of a small city, whirling around so fast its surface is moving at a significant fraction of the speed of light. This furious spin powers everything we see. Like a cosmic lighthouse, it shoots out twin beams of radiation and particles from its magnetic poles. Every time one of those beams sweeps past Earth, our telescopes detect a pulse of energy, a heartbeat from a stellar corpse. This clockwork precision is what makes it so famous and so studied, but this clock is broken. It suffers from what astronomers call glitches. Without warning, the pulsar's spin will suddenly, violently speed up. In a fraction of a second, its rotation period can shorten by a tiny but measurable amount. It is as if a spinning ice skater suddenly pulled their arms in without any effort. These glitches are catastrophic events on a stellar scale, releasing more energy than our sun puts out in weeks. They are the key to the greatest mystery of all: what is inside this thing. We cannot see past its surface. Our best models suggest the interior is a bizarre quantum soup, a superfluid of neutrons that can flow without any friction, surrounding a possibly solid core. During a glitch, it is thought that this inner superfluid, which spins at a different rate, suddenly couples with the rigid crust, giving it a violent kick. But the details are pure speculation. We are observing the tremors of a world with physics we cannot replicate, listening to the heartbeat of an immortal engine whose inner workings are, and may forever remain, a beautiful enigma. That immortal engine has a terrifying temper. The second strange phenomenon rips apart our understanding of how cosmic accelerators work. In 2011, the Fermi Gamma Ray Space Telescope witnessed something impossible. The entire Crab Nebula, a structure light-years across, suddenly began to glow with intense gamma rays, not in a slow build-up over weeks, but in a violent outburst that peaked in mere hours. Imagine a city the size of a continent, and every single light in it flickers on at the exact same moment. That is the scale of what happened. These are not the steady pulses from the spinning neutron star. These are giant, chaotic flares that overwhelm the entire system. The energy involved is almost incomprehensible. To produce gamma rays this powerful, electrons must be whipped up to velocities within a fraction of a percent of the speed of light. Our standard model for this, called Fermi acceleration, involves particles bouncing back and forth across shockwaves, slowly gaining speed like a ball in a cosmic pinball machine. But that process takes time, days or weeks. The Crab's flares happen in a single afternoon. This means there is a shortcut, a particle accelerator of unimaginable efficiency operating right next to the pulsar. The leading suspect is a process called magnetic reconnection. Picture the pulsar's immensely twisted magnetic field lines strained like over-wound rubber bands. If they snap and reconnect, they can release catastrophic amounts of energy all at once, catapulting particles to their extreme speeds in an instant. But this is magnetic reconnection on a scale we cannot fathom, with forces that make solar flares look like static electricity. These flares are a direct message, a declaration that in the heart of this beautiful nebula, there is a zone of physics we have not yet written the rules for. A place where nature has found a way to break its own speed limit for energizing matter. Those flares are just the prelude to a larger, visible dance. The third phenomenon is written across the nebula itself in strokes of ghostly light. Look at any detailed image from the Hubble Space Telescope, and you will see them, delicate filaments and ripples that look like brushstrokes on a cosmic canvas. Astronomers call them the wisps. They are not permanent features, not mere clouds of gas. They are alive with motion. Time-lapse observations from Hubble and the Chandra X-ray Observatory reveal a breathtaking spectacle. These luminous structures form, rush outward, and then fade away, all within weeks or months. Their speed is what defies belief. Some of these wisps have been clocked moving at half the speed of light. To put that in human terms, a wisp could travel from Earth to the Moon in about 2.5 seconds. We are watching something the size of a solar system move at a pace reserved for subatomic particles in our largest accelerators. The prevailing theory is that we are seeing shock waves. Remember the pulsar wind, that hurricane of particles blasted out from the spinning neutron star. It screams outward until it slams into the slower-moving shell of gas ejected from the original supernova. That collision point is a standing shock wave, a wall of energy. The wisps are thought to be ripples or knots within this chaotic frontier, regions where magnetic fields are pinched and particles are freshly accelerated, causing them to glow brilliantly. But the theory quickly meets its limits. Why do these features form in such distinct, sometimes ring-like patterns? Why do they move in fits and starts, sometimes appearing in one location only to vanish and reappear somewhere else entirely? Their behavior is less like a smooth wave on a pond and more like the chaotic froth where a raging river meets the ocean. The precise recipe that takes the pulsar's raw, furious wind and sculpts it into these fleeting, relativistic artworks remains one of the nebula's most beautiful unsolved equations. We can see the artist's brush moving, but we cannot yet understand the hand that guides it. This furious activity focuses into a single, brilliant point of mystery. Zooming in with the Chandra X-ray Observatory, astronomers found a feature so intense it outshines everything around it. Phenomenon 4 is the anomalous X-ray knot. It is a tiny, searingly bright clump of material sitting terrifyingly close to the pulsar itself. In the violent chaos of the nebula, this one spot shines with a concentrated, unwavering rage in X-ray light. Its sheer luminosity is the first clue that something extraordinary is happening here. The leading theory is a compelling one, that we are looking at the termination shock. This is the theoretical wall, the exact point where the pulsar's relativistic wind meets the resistance of the surrounding nebula and is abruptly slowed down, converting its immense kinetic energy into the radiation we see. Think of it as the cosmic equivalent of a sonic boom, but for particles moving at nearly the speed of light. This knot should be the ground zero of that collision. Yet, for all the elegance of this idea, the knot refuses to behave perfectly. Its brightness fluctuates in ways that are hard to explain with a simple shock model. Its shape and precise location are just slightly off from where our best simulations predict the termination shock should be. Is it a particularly dense clump of material in the nebula causing an especially violent interaction? Could it be a kink or a twist in the pulsar's magnetic field, focusing the wind into a devastatingly bright jet? Or is it something else entirely, a structure we have not even named yet? The Chandra images present us with a paradox, a landmark so bright we cannot miss it, yet whose foundational role in the nebula's machinery we still cannot confirm. It is a glaring signpost in the cosmic fog, pointing toward a truth we have not quite reached. But the true scale of this cosmic engine is a matter of perspective. If you could see the Crab Nebula with radio eyes, its true size would shock you. The fifth strange phenomenon is the radio halo size paradox. When astronomers point radio telescopes like the Very Large Array toward the Crab, they see something much bigger than the beautiful, intricate cloud captured by Hubble. The nebula's radio-emitting region extends far beyond the visible filaments and even beyond the brilliant X-ray glow mapped by Chandra. It is a vast, faint halo, a ghostly echo of the explosion that continues to expand into space. This discrepancy is a direct clue to the life story of the particles within the nebula. The brilliant visible light and X-rays come from the youngest, most energetic electrons. These are the freshly accelerated particles screaming through the magnetic fields near the pulsar and its shock waves, emitting high-energy radiation as they are whipped around. But electrons lose energy over time. As they age and slow down, they emit radiation at lower and lower frequencies, eventually shining brightest in the radio part of the spectrum. The giant radio halo is the graveyard of these ancient particles. They have diffused outward, drifting far from the violent central engine that created them, painting a much larger portrait of the supernova's aftermath. The strangeness lies in the journey. How do these older electrons travel so far? Our models of particle transport within the nebula's tangled magnetic fields struggle to explain the sheer size and smoothness of this radio halo. It suggests that magnetic fields act not just as cages, but as highways, allowing particles to seep into interstellar space in ways we do not fully understand. Furthermore, the sharp boundaries we see in X-rays and visible light become soft, fading edges in radio waves. This tells us that the nebula is not one object with a single border, but a layered history book. Each wavelength of light reveals a different chapter, a different population of particles with its own story of energy and escape. A composite image combining radio, visible, and X-ray light would show a brilliant, complex heart surrounded by a colossal, fading aura. This paradox forces a humbling realization that even for an object we have studied for centuries, we are still learning how to see its full, hidden shape. The light itself carries a hidden message about the forces shaping this chaos. Phenomenon 6 is the changing polarization patterns. When we look at the Crab Nebula, we are not just seeing light, we are seeing light that has been imprinted with the signature of immense magnetic fields. Think of light as a wave vibrating in all directions. A strong magnetic field can force those vibrations to align in a single plane, like combing messy hair into neat parallel lines. This is polarization. By measuring it, astronomers can essentially map the invisible magnetic field lines threading the nebula. What they find is not a simple, orderly pattern. Instead, the polarization vectors paint a picture of magnificent turmoil. Overlaid on images of the nebula, they look like a swirling, chaotic fingerprint. Some regions show field lines stretched taut, pointing directly away from the pulsar like spokes on a wheel. In other areas, the vectors twist into knots or form whirlpool-like eddies. And this map is not a permanent one. It changes over months and years. We are watching the magnetic skeleton of the nebula writhe and reconfigure itself in real time. The source of this field is the pulsar wind, that hurricane of charged particles. As this wind expands, it stretches the pulsar's magnetic field out into the nebula like pulling taffy. But the process is far from smooth. The collision with the slower supernova debris, the formation of shock waves, and the turbulent motions of the gas all twist, fold, and amplify the field in ways that are devilishly hard to predict. Our most sophisticated computer simulations can reproduce the broad strokes, but they fail to capture the intricate, dynamic lacework we actually observe. The polarization patterns tell us the magnetic field is not a passive scaffold. It is an active, living component of the nebula's engine. It channels particles, focuses energy, and likely plays the starring role in creating those mysterious flares and wisps. Yet its precise topology, the three-dimensional shape of every loop and knot, remains a turbulent secret written in polarized light. We can read the language, but we are still translating the poetry of its violent, beautiful structure. Those magnetic fields are sculpting a landscape where the very rules of shock waves seem to break down. Phenomenon 7 is the case of the missing reverse shock. In a typical supernova remnant, the physics follows an elegant two-step dance. First, the blast wave from the explosion rockets outward, plowing into the interstellar medium like a snowplow. But then, a second wave forms called the reverse shock. This wave travels backward, back into the expanding shell of stellar debris itself, heating it up and causing it to glow brightly in specific wavelengths of light. It is a standard feature, a cosmic echo expected in nearly all such explosions. The Crab Nebula, true to form, ignores the standard. Evidence for a clean, classic reverse shock here is frustratingly weak and deeply confusing. Our telescopes see plenty of glowing gas, but its structure and motion do not match the neat, inward-moving spherical shell the models predict. Instead, the interaction appears brutally direct and wildly turbulent. The culprit is the pulsar wind. In most remnants, the central neutron star is quiet or spins slowly, allowing the simple blast wave physics to dominate. But the Crab's pulsar is a screaming powerhouse. Its relentless, supersonic wind punches into the supernova ejector from the inside, creating a complex, churning mess of shocks and eddies right from the start. Imagine the difference between a firecracker exploding in still air, creating a neat spherical shock, and a jet engine pointed directly into that expanding fireball. The Crab is the jet engine scenario. The pulsar wind is so intense it may have disrupted or even completely overwhelmed the formation of a traditional reverse shock, shredding it into a multitude of smaller, chaotic interactions. If you could watch a schematic animation, a standard model would show a smooth, expanding bubble with a second, concentric shell moving neatly inward. The Crab's proposed structure would look more like a furious, boiling cauldron, with fingers and filaments of energy lashing out from the center, violently stirring the pot. This missing shock is not just an absent detail, it is a profound clue. It tells us that in the Crab, the corpse of the star did not just sit quietly in its tomb. It woke up almost immediately, seized control of its own aftermath, and began rewriting the physics of its expansion with a relentless, particle-driven gale. The expected echo never came because the central engine never stopped shouting. That furious wind may have swept the crime scene almost clean. The eighth strange phenomenon is a case of a missing shell. In a typical supernova remnant, especially one as young as the Crab, the most prominent feature is a brilliant, expanding bubble. This is the blast wave itself, a spherical shell of shocked gas glowing brightly as it plows through space. It is the signature of the explosion, the visible border of the event. The Crab Nebula, however, presents us with a ghost. Its optical shell is astonishingly faint, so subtle it was only confirmed in detail in the late 1990s using the most advanced telescopes and image processing techniques. Where we expect a sharp, luminous rim, we find only the faintest whisper of a boundary. This presents a direct and puzzling question. Where did all the material from the exploded star go? A star that massive should have ejected a sun's worth of material, enough to form a thick, bright shell. One theory is that the supernova itself was unusually low in energy, a faint whisper rather than a definitive shout, leaving less ejector to form a bright shell. But the pulsar at the center tells a different story. Its incredible spin suggests the core collapse was violent. The more compelling suspect is the very wind we have been discussing. From the moment it formed, the pulsar's relentless gale of particles began pushing outward from the inside. Instead of a simple expanding shell, think of it as a balloon being inflated from within. The pulsar wind has acted like a cosmic bellows, inflating the nebula and pushing the stellar debris outward, but also spreading it incredibly thin. It has taken the material that should form a crisp, bright shell and diluted it into a vast, diffuse halo that is almost invisible to our eyes. Deep, processed images from observatories like the Subaru telescope in Hawaii tell this story. They reveal an immense, faint glow extending far beyond the famous tangled filaments, a ghostly outline of the true scale of the catastrophe. This faint shell is not a failure of the explosion, but a testament to the power of the engine it left behind. The pulsar did not just inherit the aftermath, it actively reshaped its own tomb, blowing the walls so wide and thin they nearly vanished from view. But the faintness of its shell is not the only ghost haunting this explosion. The ninth strange phenomenon lies in the very chemistry of its corpse. When astronomers point their spectrometers at the glowing filaments of the crab, they are doing cosmic forensics. They break the light down into its constituent colors, its spectrum, looking for the telltale fingerprints of specific elements. Each element, like helium, carbon, or oxygen, emits light at precise, unique wavelengths. By measuring the brightness of these spectral lines, scientists can weigh the nebula, determining exactly how much of each element was forged in the star and scattered by the blast. The results are a profound conundrum. The observed ratios of these elements do not perfectly match what our best models predict for a core collapse supernova from a star of its estimated mass. It is as if a master chef followed a famous recipe, but the final dish has a subtly different flavor profile than anyone expected. The strangeness is in the details. Perhaps the progenitor star, before its death, underwent unusual episodes of nuclear burning in its final millennia, altering the layers of elements in its core in ways our stellar evolution codes do not yet capture. Or more violently, the explosion itself may have been messy. Theoretical models often assume a relatively clean, spherical blast, but what if the detonation was lopsided, or if fierce turbulence during the collapse churned the star's interior, mixing the onion like layers of silicon, oxygen, and neon before they were ejected? This would scramble the expected chemical signatures. A graphic comparing the observed elemental spectra from the nebula to the smooth, predicted curves from theory would show mismatched peaks and valleys, a direct visual proof of our incomplete understanding. The filaments are not just beautiful clouds, they are the final, frozen testimony of the star's last moments, and that testimony contains contradictions. It suggests that the star did not die a textbook death, but one with unique, violent twists that left an indelible mark on the elemental makeup of its remains. We are reading the last will and testament of a giant, and some of the clauses simply do not make sense with the laws we have written for it. The chemical contradictions in the filaments are just one layer of a deeper, more violent truth. Phenomenon 10 is the acceleration of ultra-high energy particles. The Crab Nebula is not just glowing with light, it is firing bullets. Specifically, it is a confirmed source of particles with energies in the peta-electronvolt range. To grasp that scale, a single one of these particles carries the kinetic energy of a professionally served tennis ball. Imagine a subatomic speck, a proton or a heavy ion, packing the punch of a physical object you could hold in your hand. These are some of the most energetic particles we have ever traced back to a specific source in our galaxy, and their existence here poses a monumental puzzle. How does this nebula, this chaotic cloud, act as a particle accelerator more powerful than anything we could ever build on Earth? Our standard model for this, called diffusive shock acceleration, is elegant but too slow. It relies on particles bouncing back and forth across a shock wave, gaining a tiny bit of energy with each crossing, like a ball being volleyed between two approaching walls. But to reach peta-electronvolt energies within the crab's relatively small size and young age, this process is simply not efficient enough. The particles would need to travel a distance greater than the nebula itself to gain that much speed. So the crab must be cheating. It must possess a shortcut, a hyper-efficient mechanism that bypasses the slow, stately rules. The prime suspects are the same violent processes we have already glimpsed. Could it be those sudden, catastrophic flares caused by magnetic reconnection? In those moments when magnetic field lines snap and reconnect, they could create electric fields of unimaginable strength, capable of slinging particles to these extreme energies almost instantaneously. Or perhaps it is the immense, chaotic turbulence within the nebula. The swirling, twisting magnetic fields could act like a vast network of pinball bumpers, randomly but violently kicking particles to higher and higher speeds in a stochastic frenzy. We do not yet know the answer, but we have the evidence. Ground-based observatories like the High-Altitude Water Cherenkov Observatory and the Large High-Altitude Air Shower Array do not look at the crab directly. Instead, they watch for the faint, expanding showers of secondary particles created when these ultra-high-energy bullets slam into Earth's atmosphere. By tracing the paths of these showers back to their origin, they point an undeniable finger at the Crab Nebula. It is a cosmic gun, and we are standing in the line of fire, studying the spent shells to understand the impossible weapon that fired them. The bullets it fires are not the only invisible energy it radiates. Phenomenon 11 is the infrared excess mystery. When astronomers measure the crab's light across the entire electromagnetic spectrum, from radio waves to gamma rays, a clear pattern should emerge. The brilliant glow from its synchrotron radiation, that light created by electrons spiraling in magnetic fields, follows a predictable curve. It should rise and fall in intensity across different frequencies like a smooth, sloping hill. But when we look in the infrared, the data reveals a bump. The crab is emitting significantly more infrared light than the synchrotron model alone can explain. It is as if you are listening to a symphony and amidst all the violins and cellos, you suddenly heard the clear, distinct sound of a flute that no one in the orchestra was playing. This infrared excess is a signal of something else, something different, mixed into the nebula's furious particle storm. The leading candidate is dust. Not the dust in your house, but cosmic dust, microscopic grains of carbon and silicates, like tiny pieces of sand or soot. These grains absorb energy and re-radiate it as heat, glowing warmly in the infrared. This presents a fascinating puzzle. How can there be warm dust in the heart of a supernova remnant that is only 1,000 years old? A supernova explosion is the most violent event in the universe, a blast wave of energy that should vaporize any solid material for light years around. So where did this dust come from? There are two compelling and equally strange possibilities. First, it could be pre-existing dust, a ghost from the star's past. In its final centuries, the massive progenitor star may have shed huge amounts of its outer atmosphere in powerful stellar winds. This ejected material could have cooled and condensed into dust grains far from the star, forming a vast, dusty shell. When the star finally exploded, the blast wave might have plowed through this pre-made dust, shock heating it but not completely destroying it, leaving it to glow in the infrared. The second possibility is even more astonishing. The dust might be brand new. As the expanding cloud of supernova ejecta expands and cools, the conditions in certain dense, shielded knots of gas could become just right for atoms to stick together and form solid particles. This would mean we are witnessing the very first steps of cosmic recycling in real time, watching the ashes of a dead star begin to coalesce into the building blocks of future planets and perhaps life. Composite images from space telescopes like Spitzer and Herschel highlight this mystery beautifully. In visible light, the crab is a tapestry of glowing filaments. But in the infrared, a different structure emerges, a more diffuse, warm glow that sometimes aligns with the filaments and sometimes fills the spaces between them. This hidden component tells us that amidst the relativistic fury, a quieter, more material process is also at work. The Crab Nebula is not just an accelerator and a lighthouse, it is also a cosmic forge, silently working to transform the aftermath of destruction into the seeds of something new. Yet this silent forge of dust operates within a structure of startling geometric clarity. The 12th strange phenomenon is written in the very silhouette of the nebula. In the iconic Hubble images, the crab is not a perfect oval. On opposite sides of its glowing body, you can see two distinct indentations, like gentle bites taken out of its luminous edge. Astronomers call these features the optical bay and the counter bay. They are not random imperfections, they are a matched set, symmetrical yet subtly offset from each other, creating a profound and elegant asymmetry in the nebula's expansion. If you drew a line through the pulsar at the center, you would find one bay on one side and its counterpart not directly opposite but rotated slightly. This precise misalignment is the heart of the mystery. It suggests an underlying order, a hidden hand guiding the nebula's growth in a specific, lopsided way. One leading theory points an accusing finger at the interstellar medium, the thin soup of gas and dust that fills the space between stars. Perhaps the expanding nebula is not plowing into a perfectly uniform void. It might be encountering a slight density gradient, a gentle cosmic slope. The bay could be where the nebula is encountering slightly denser material, slowing its expansion in that specific region, like a balloon pressed against a wall. But this does not easily explain the clean, matching shape of the counter bay on the opposite side. Another, more compelling idea involves the invisible architecture of magnetic fields. The pulsar's wind may not be blowing equally in all directions. It could be channeled, focused by an asymmetric magnetic field into a more equatorial outflow. This would inflate the nebula more vigorously around its middle, while the poles, where the bays are located, expand more slowly and might even be pinched inward by external pressure. An annotated Hubble image makes this puzzle visually arresting. Two graceful, shadowy curves are marked on the brilliant oval, a clear testament that the nebula's beautiful chaos is constrained by a hidden geometry. The persistence of these features over decades of observation tells us this is not a temporary ripple, but a fundamental property of its structure. The bays are a cosmic signature, a lasting impression left by forces we can model, but whose precise combination we cannot yet replicate. They are the visible proof that even in apparent disorder, the Crab Nebula is obeying a set of rules we have not fully decoded. This elegant asymmetry hints at a deeper motion we can barely perceive. Phenomenon 13 is the proper motion mismatch, a clue hidden in the slow drift of the nebula's outer filaments. By comparing high-resolution images taken decades apart, astronomers can track how individual knots of gas are moving across the sky. They measure their proper motion, their sideways movement from our point of view. Combine this with the nebula's known distance, and you can calculate their true, three-dimensional expansion speed. The results are startling. The outer filaments appear to be moving too fast. If you simply take their current speed and rewind the clock, you would find they left the site of the explosion long before the year 1054, the historical date of the supernova. It is a chronological paradox, as if the smoke from a gunshot started rising before the trigger was pulled. One potential resolution is that our distance measurement to the crab is slightly off. Astronomy is built on a ladder of distance estimates, and if the crab is actually a bit closer to us than we think, then the filament's motions would translate to lower actual speeds, solving the timeline issue. But adjusting the distance is a delicate act, as it would ripple through every other calculation about the nebula's energy and the pulsar's power. The more intriguing explanation involves a history of acceleration. We have been thinking of the nebula's expansion as a single, smooth event, like a balloon inflating at a constant rate. But what if the pulsar wind, that relentless central engine, did not turn on immediately at full strength? Perhaps in the first few decades or centuries after the explosion, the expanding shell coasted outward under its own initial momentum. Then, as the pulsar wind ramped up to its current ferocious power, it began to catch up to and push on the inner surface of that shell, giving the entire nebula an extra kick, a second stage of acceleration. This would mean the filaments we see today are not moving at the speed of the initial blast, but at a higher speed imparted later. A graphic showing this would be powerful. First, a simple animation of concentric circles expanding at a constant rate from a central point, rewinding neatly to the year 1054. Then, a second, more complex animation. The initial shell expands, but then a powerful wind erupts from the center, represented by a wave of color, catching up to the shell and shoving it faster, making the rewind timeline overshoot the known date. This dynamical mystery forces us to see the crab not as a fossil of a single instant, but as an object with a complex biography, its expansion history written in the conflicting speeds of its fleeing fragments. The proper motion mismatch is a speedometer reading that tells us we have misunderstood the journey, even if we know the destination. This chronological paradox is echoed by a flicker in its very color. Phenomenon 14 is the variable ultraviolet output. Beyond the violent gamma-ray flares, the entire nebula's glow in the ultraviolet part of the spectrum is not a steady light. It rises and falls in unpredictable, subtle ways. This is a crucial distinction. The pulsar's own clockwork pulses are one thing, a predictable heartbeat. But the nebula's changing ultraviolet light is something else entirely. It means the vast cloud of gas and particles itself is changing its brightness, as if the fog in a valley were growing thicker and thinner on its own. This variability points directly to the lifeblood of the nebula, its population of ultra-high energy electrons. Ultraviolet light is produced by electrons with slightly less energy than those making X-rays, but still far more energetic than the ones creating visible light. For the nebula's ultraviolet output to change, the number or the distribution of these specific electrons must be shifting in real time. Imagine a vast field of fireflies all glowing with a specific blue-white light. If the overall brightness of the field flickers, it means fireflies are being born or dying, or perhaps being herded into denser clusters. In the crab, the magnetic field is the herder. Its dynamic, writhing structure, which we mapped through polarization, is constantly reconfining and re-accelerating particles. A sudden tightening of magnetic field lines in one region could squeeze electrons together, increasing their collisions and their ultraviolet glow. Conversely, a region where the field temporarily weakens might allow electrons to escape, dimming that patch of the nebula. The ultimate source of this chaos is the pulsar's erratic energy injection. Every glitch, every subtle shift in its wind, sends a new wave of turbulence through the system. Light curves from ultraviolet telescopes like NASA, Swift, or the Hubble Space Telescope tell this story in jagged lines. They do not show the clean, periodic spikes of the pulsar, but a messy, rolling landscape of brightness, a direct readout of the nebula's turbulent metabolism. This confirms the crab is not a static monument. It is a living nebula, its light a vital sign that is never constant, breathing with the erratic heartbeat of the corpse at its center. This relentless breathing is powered by a river of pure energy. The 15th strange phenomenon is the pulsar wind itself, a cosmic hurricane blowing from a city-sized star. Picture not a gentle breeze, but a near-light-speed torrent of charged particles, mostly electrons and their antimatter twins, positrons, all woven through with a spiraling magnetic field of unimaginable strength. This wind is the direct output of the pulsar's furious spin, a conversion of rotational energy into a particle gale so powerful it alone lights up the entire nebula, making it shine brighter than 100,000 suns. The strangeness lies in its transformation. Close to the neutron star, within just a few hundred kilometers, the wind is thought to be a highly magnetized, perfectly smooth flow, like a laser beam of pure magnetic force. But as it screams outward, something fundamental changes. The energy stored in those wound-up magnetic fields must be transferred to the particles themselves. This transition from a magnetically dominated wind to a kinetic particle-dominated wind is one of the great unobserved processes in astrophysics. We know it happens because we see the results, the brilliant glow of particles moving at relativistic speeds, but we have never directly seen the moment of handoff. It is like watching a river emerge fully formed from a hidden spring, never witnessing the water actually bubbling up from the ground. Artistic representations of this are both beautiful and speculative. They often show the pulsar as a tiny, brilliant point, with ethereal spiral lines representing its magnetic field flowing outward like the arms of a galaxy. These lines grow more chaotic as they expand, eventually dissolving into a turbulent haze of particles that slam into the nebula's inner boundary, creating a shimmering wall of light. This collision zone is the standing shock wave, the place where the wind's orderly, supersonic rush meets an immovable obstacle and is forced to release its catastrophic energy as radiation. The composition of this wind adds another layer of mystery. Is it truly a perfect balance of matter and antimatter, electrons and positrons, or are there heavier particles mixed in? The answer would tell us about the extreme physics happening at the pulsar's surface, perhaps even about pair production, where raw energy spontaneously creates particle-antiparticle pairs in the intense magnetic field. The pulsar wind is the invisible breath of the stellar corpse, a breath that sculpts the glowing tomb around it and whose deepest secrets remain locked in a region of space too small and too violent for our telescopes to resolve. But that brilliant, chaotic light carries a hidden fingerprint of its own. Phenomenon 16 is the synchrotron spectrum break, when astronomers plot the Crab's brightness across every frequency, from the deep hum of radio waves to the searing scream of gamma rays, they expect a smooth, sloping curve. This is the signature of synchrotron radiation, the light given off by electrons spiraling in magnetic fields, but the Crab's plot reveals a subtle yet crucial kink. In the high-energy X-ray region, the curve noticeably bends like a highway that suddenly changes gradient. This is the spectral break, and it is a direct message about the life and death of the nebula's electron population. The shape of this curve tells a story of balance between two cosmic forces, acceleration and loss. Electrons are constantly being whipped up to fantastic speeds by the nebula's unseen engines. But they are also constantly losing energy, bleeding it away as the very synchrotron light we are observing. The break marks the energy where these two processes, gain and loss, finally reach a stalemate. Below the break, electrons have time to be accelerated and fill out a predictable distribution. Above the break, the losses are so severe that even the nebula's mighty accelerators cannot push the electrons to significantly higher energies for long. They radiate away their power almost as fast as they receive it. Think of it like trying to fill a bucket with a hole in the bottom. You can pour water in, but once the hole is a certain size, the water level cannot rise any higher, no matter how fast you pour. The break is that water level. The mystery is in the precise details of the hole and the faucet. Does the break represent the absolute maximum energy the central pulsar can impart? Or is it a sign that the acceleration process itself becomes less efficient at higher energies? Perhaps it marks the point where electrons begin to escape the nebula entirely, fleeing before they can be accelerated further. Our best models can approximate the break, but they cannot perfectly reproduce its exact shape and location. A simple graph makes this puzzle clear. On one axis, the energy of the light from radio to gamma. On the other, the brightness. A smooth, simple curve would be a single, graceful arc. The Crab's real data, however, would show two distinct lines with different slopes connected at a sharp elbow in the X-ray band. This kink is a fundamental boundary in the Crab's ecosystem, an energy ceiling written in light, revealing the limits of its most violent processes. That spectral break is a boundary, but it is not the final frontier for the Crab's power. Phenomenon 17 takes us to the very edge of what we can see, into the realm of tera-electronvolt gamma rays. These are photons with energies a trillion times greater than visible light, the signature of the most extreme particle accelerators in the cosmos. When specialized ground-based telescopes like Veritas and HESS stare at the Crab, they do not capture a picture in the traditional sense. They detect the faint, fleeting flashes of Cherenkov light produced when these gamma rays slam into our atmosphere. From thousands of these flashes, they can painstakingly reconstruct a map, a gamma ray image of the nebula. And what they reveal is profoundly strange. The shape of the Crab in these monstrously energetic gamma rays does not match its shape in X-rays. If you placed two images side by side, the difference would be startling. The Chandra X-ray image shows a brilliant, compact torus, a donut of furious activity around the pulsar, with jet-like structures spewing from its poles. It is intricate, sharp, and concentrated. The Terra electron-volt gamma-ray image, however, is more like a diffuse, extended cloud. It is larger and smoother, with its brightness distributed in a broader, less structured halo. This mismatch is a direct clue that the story we have been telling is incomplete. We have assumed that the particles are accelerated in one central zone, near the pulsar wind shock, and then spread out, losing energy as they go. But these images tell a different tale. The fact that the highest energy gamma rays come from a larger, different-shaped region suggests that the particles producing them might have a different history. Perhaps they are not accelerated at the central shock at all, but somewhere else entirely. One compelling idea is that the highest energy particles, likely protons or heavier atomic nuclei, are accelerated further out, in the turbulent, chaotic regions where the nebula's expanding shell interacts with the surrounding interstellar medium. Another possibility is that even if electrons are responsible, they are being re-accelerated in these outer zones, given a second, tremendous kick far from the pulsar itself. Imagine a factory with two different assembly lines. One line in the center produces brilliant X-ray emitting electrons with incredible efficiency. The other line, operating in the sprawling outskirts, specializes in forging the ultra-rare Terra electron-volt monsters. They share a power source, the pulsar, but their workshops and their blueprints are distinct. These gamma-ray images force us to redraw our mental map of the Crab's engine room. It is not a single, neat accelerator with a simple fallout zone. It is a hierarchical, multi-stage complex with different assembly lines for different particle energies, operating in different parts of the vast, turbulent structure. The most violent products of this cosmic factory are not made at the central forge, but in the sprawling industrial parks at its edges. But even the sprawling edges of this factory are not the end of its influence. Phenomenon 18 is the silent, invisible friction of the interstellar medium. The Crab Nebula is not expanding into a perfect, empty void. Space is filled with a whisper-thin gas, mostly hydrogen, dotted with occasional wisps of denser material. This is the interstellar medium, and the Crab is plowing through it like a ship through a ghostly sea. This subtle interaction, happening at the nebula's outermost frontier, is one of the most difficult things to observe, yet it holds the key to its ultimate fate. The evidence is maddeningly indirect. We cannot see a sharp bow shock, a brilliant wall of compressed gas, like we see around some faster-moving supernova remnants. The Crab's expansion is relatively slow, and its surrounding medium is extremely tenuous. Instead, the clues are in the asymmetries. The optical bays, those gentle indentations on the nebula's sides, could be where the expanding shell is encountering slightly denser patches of interstellar material, slowing its progress in those spots. The vast, faint radio halo might also be shaped by this external pressure, its particles piling up against an invisible wall. To visualize this, imagine an animation of the nebula as a glowing, expanding bubble. Superimposed over it, in a faint, translucent blue, are wispy, irregular clouds representing the interstellar medium. As the bubble grows, its leading edge presses against these clouds, deforming slightly, creating dents and ripples on its otherwise smooth surface. This is the cosmic environment in action. The mystery lies in mapping this invisible boundary. Our telescopes see the bright emission from the nebula itself, but seeing what lies just beyond, the material that is being swept up and heated, is a monumental challenge. It requires looking for extremely faint signatures, perhaps in specific wavelengths of ultraviolet light or in the subtle distortion of background starlight. Understanding this interaction is not just about the crab's present shape, it is about its long-term evolution. Over tens of thousands of years, this gentle friction will be what ultimately slows the nebula's expansion to a halt. The kinetic energy of the blast will be gradually transferred to heating the surrounding gas, and the brilliant filaments will fade, their material mixing back into the galactic reservoir to form new stars. The crab is not an isolated monument. It is in a constant, quiet dialogue with its environment, and the shape of its ghostly tomb is being written in part by the faintest whispers of the galaxy it calls home. Its historical record is written in daylight. Phenomenon 19 confronts us with the eyewitness accounts from the year 1054, when Chinese, Japanese, Arab, and possibly Native American astronomers all recorded the sudden appearance of a new star in the constellation of Taurus. Their reports are not vague mentions. They state clearly that this guest star was visible in broad daylight for 23 consecutive days, shining with a brilliance rivaling the planet Venus, and remaining visible to the naked eye at night for nearly 2 years. From a modern scientific perspective, this presents a subtle but profound puzzle. When we take the Crab Nebula's current distance, about 6,500 light-years, and combine it with our best models for a standard core collapse supernova, the calculated brightness sometimes falls just short of explaining such a prolonged, dazzling daytime visibility. It is a discrepancy of perception versus calculation, a hint that the star's death scream may have been even more spectacular than our physics allows. One compelling explanation involves the environment of the explosion itself. Perhaps the progenitor star, in its final millennia, expelled a dense, slow-moving shell of gas. When the supernova blast wave later caught up and smashed into this pre-existing shell, the resulting collision would have dumped a colossal amount of extra energy into visible light, creating a temporary, brilliant boost in luminosity. This would be like a firework exploding inside a glass sphere, the containment focusing and amplifying the flash. Another possibility is a light echo. Even today, faint reflections of the 1054 event, caused by its light scattering off interstellar dust clouds hundreds of light-years away from the nebula, are still detectable. But in the immediate aftermath, such echoes could have subtly enhanced the apparent brightness and duration of the event from our vantage point on Earth. A third, simpler idea is that our view was simply clearer then. The line of sight between Earth and the Crab Nebula is not perfectly empty. If the interstellar dust that dims starlight was slightly less dense 1,000 years ago along that specific path, the supernova would have appeared correspondingly brighter to those ancient watchers. We can picture the scene: an astronomer of the Song Dynasty court stepping onto a balcony at noon, pointing to a piercing white star where none had been before, a silent oasis of light in the blue sky. That recorded brilliance is not just a historical footnote, it is a data point. It forces us to question whether our models for the explosion are complete, or if we need to inject more violence, more complexity, into that ancient cataclysm to make the numbers align with the awe felt by human eyes a millennium ago. The light we see is woven from invisible threads. Phenomenon 20 is the filamentary braiding of magnetic fields. When we zoom into the crab's most delicate structures, the thread-like optical filaments that give the nebula its name, we find a hidden architecture of stunning complexity. New, ultra-high-resolution studies from telescopes like Hubble suggest the magnetic fields within these glowing tendrils are not simple, straight lines. They appear to be intricately braided, twisted, and intertwined like the strands of a cosmic rope. This fine structure is a direct challenge to our understanding of how such order emerges from chaos. The standard picture is that the pulsar's wind stretches the magnetic field out into radial lines like spokes from a hub, but braiding implies a turbulent, dynamic history of interaction. As the expanding gas from the supernova collides with itself and with the pulsar wind, it creates whirlpools and eddies. These chaotic motions can twist and fold the magnetic field lines, wrapping them around each other, amplifying their strength through a process called dynamo action. Imagine taking two separate strands of string, laying them parallel, and then gently twisting them together. Now imagine that process happening in a churning, supersonic fluid of gas and particles, driven by the spin of a neutron star. The resulting magnetic ropes are not just beautiful, they are powerful. This braided structure can store immense energy and may be the key to explaining how particles are confined and accelerated within the filaments themselves. It could be the very mechanism that prevents the nebula's high-energy electrons from instantly escaping, trapping them long enough to produce the brilliant glow we see. Simulating this in a computer is a Herculean task. It requires modeling fluid dynamics, magnetic forces, and particle acceleration all at once, across scales from light years down to astronomical units. Our most advanced simulations can produce tangled fields, but replicating the specific rope-like braiding observed in the crab's finest threads remains just beyond our reach. An artist's illustration based on this data would be mesmerizing. Over a breathtaking Hubble close-up of luminous, knotted filaments, we would see superimposed lines of force, not as neat parallel strokes, but as woven, helical structures curling around the gas-like vines on a trellis. This braiding is the signature of a deep and ongoing conversation between matter and magnetism, a conversation that began 1,000 years ago and whose intricate grammar we are only now beginning to decipher. That intricate braiding of forces may occasionally come undone. Even the most reliable clock in the cosmos can fail. Phenomenon 21 is the pulsar's off-states in radio waves. For all its legendary precision, the 30 times a second heartbeat of the Crab pulsar is not absolutely perfect. In the radio part of the spectrum where it was first discovered, the pulsar occasionally and without warning simply stops. For days or even weeks at a time, the steady pulse of radio waves from that spinning neutron star vanishes completely, as if someone threw a switch. These are nulling events, and they shatter the illusion of cosmic perfection. Imagine listening to a metronome that has ticked flawlessly for decades. Then, one day, it just goes silent. You wait, and just as you begin to fear it is broken forever, the ticking starts again, perfectly on beat, as if nothing had happened. That is the unnerving reality of the Crab pulsar. The mystery is not that it happens, but why. What could possibly cause a stellar engine of that power, spinning with that ferocious momentum, to cease broadcasting in one specific type of light? The theories point to drama in the pulsar's immediate vicinity, its magnetosphere. This is the region of space dominated by its immensely powerful magnetic field, filled with a seething plasma of electrons and positrons ripped from the star's surface. One idea is a sudden restructuring of this magnetic field. Perhaps the twisted lines snap and reconnect in a new configuration that temporarily shuts down the mechanism that generates the radio beam, like a kink in a garden hose stopping the flow. Another possibility is a plasma instability, the flow of charged particles above the magnetic poles which creates the lighthouse beam we see could become turbulent or choked, interrupting the signal. A third, more exotic idea suggests our line of sight might be temporarily blocked. Could a dense cloud of plasma, ejected from the star itself, drift directly into the path of the radio beam, casting a shadow across the galaxy? We simply do not know. The evidence is stark. A radio pulse profile, a graph of signal strength over time, normally shows a sharp, predictable spike with every rotation. During a nulling event, that graph goes flat, no spike, just silence. Then, just as abruptly, the spikes return. This adds a profound element of unpredictability to an object we use as a celestial timekeeper. It reminds us that for all our models, we are observing the surface effects of a realm where matter exists in states we cannot create and magnetic forces operate at scales we cannot comprehend. The off states are a whisper from that hidden realm, a reminder that even a corpse spinning 30 times a second is not a simple machine, but a deeply complex and occasionally temperamental entity. The very star that died to create this cosmic spectacle is itself a missing person. Phenomenon 22 is the enduring mystery of the progenitor star. To understand the strange nebula we see today, we must first understand the nature of the giant that died. This is not a simple task, for the star itself was utterly obliterated 1,000 years ago. We are left to reconstruct its identity from the chemical clues in the debris and the nature of the pulsar it left behind. The estimates for its mass are a range, not a number, suggesting a star somewhere between 8 and 12 times the mass of our Sun. Yet the chemical fingerprints in the nebula's filaments, that mismatch we discussed earlier, tell us this was no ordinary giant. Its elemental composition hints at a life story with unusual twists. One compelling theory is that the crab's progenitor was not alone. It may have lived its life as part of a binary system, with a companion star orbiting close by. This cosmic partnership could have dramatically altered its fate. The gravitational tug of a companion could have stripped away the star's outer hydrogen layers long before its death, leaving behind a helium-rich core that exploded in a different, perhaps less energetic way. Imagine a star being slowly peeled like a cosmic orange by its partner, changing its internal structure and the very fuel available for its final detonation. Alternatively, even if it was solitary, the star might have undergone episodes of extreme mass loss through powerful stellar winds in its final millennia. This would have shed material into space, creating that pre-existing shell we suspect might have brightened the supernova and possibly provided the dust we see today. The type of pulsar left behind adds another clue. Its rapid spin suggests the collapsing core retained a significant amount of angular momentum. This is easier to explain if the progenitor star was originally spinning very fast, perhaps spun up by interactions with a binary companion. Artistic renditions of these possibilities are hauntingly beautiful. One shows a pair of brilliant stars, one massive and bloated, with a stream of glowing gas flowing from it toward its smaller companion. Another depicts a single, furious giant star, its surface boiling with titanic eruptions, casting off great plumes of material into the darkness. A third, more serene image might show a lone, blue-white supergiant, its fierce light illuminating the cosmic dust of its own making. We do not know which picture is correct. The progenitor star's true identity is the foundational mystery upon which all others are built. Its specific mass, its history of mass loss, and its possible companionship set the initial conditions for everything that followed: the violence of the explosion, the spin of the pulsar, and the very chemistry of the glowing tomb. Until we can solve this cold case of stellar evolution, the Crab Nebula remains a masterpiece whose artist's signature has faded from view. This chaotic engine of cosmic violence has become a standard candle for the universe. The 23rd strange phenomenon is the Crab Nebula's role as a celestial calibration source. For decades, astronomers have used its bright, relatively predictable glow in X-rays and gamma rays as a benchmark to tune and verify the performance of their most sensitive space telescopes. It is a trusted reference point, a lighthouse in the high-energy sky against which all other measurements are compared. The profound irony is that this object is anything but steady. We have seen its violent gamma-ray flares, its flickering ultraviolet output, and its temperamental pulsar. Its constancy is a statistical average, a smoothing out of its inherent, furious volatility over long periods of time. This creates a fascinating challenge for precision science. To use the crab as a calibration tool, astronomers must first build intricate models that account for its intrinsic variability. They must separate the true signal of their telescope's performance from the natural, erratic heartbeat of the nebula itself. It is like using a flickering, ancient candle to calibrate the finest modern light meters, requiring you to understand the exact pattern of the flicker before you can trust the meter's reading. Picture a montage in the mind's eye, a silent symphony of technology. The Chandra X-ray Observatory, the Fermi Gamma Ray Space Telescope, the Neil Gehrels Swift Observatory, and the New Star Telescope, all silently pivoting in the void, their instruments trained on the same glowing patch in Taurus. They are not just observing a mystery, they are using its chaotic light to sharpen their own vision, to ensure that when they look at fainter, more distant objects, their measurements are absolutely true. This dual identity is a testament to human ingenuity. We have taken one of the most unstable and poorly understood objects in the sky, and through painstaking observation and modeling, temporarily forced it into the role of a stable anchor. The Crab Nebula, a roiling cauldron of broken physics, has been conscripted as a tool for building the rulebook of the cosmos it so consistently defies. This reliance on the crab as a cosmic yardstick underscores a deeper, humbling truth. Phenomenon 24 is the theoretical challenge of the pulsar wind nebula. The crab is not merely a supernova remnant, it is the defining prototype of an entire class of objects, a pulsar wind nebula, where the power comes not from the fading echo of an explosion, but from the relentless gale of a spinning neutron star. For all its fame and decades of intense scrutiny, building a complete theoretical model of this object is one of the grand unsolved puzzles in modern astrophysics. The goal is to create a full, three-dimensional magnetohydrodynamic simulation, a digital twin that can accurately reproduce everything we see. This type of model must account for the fluid motion of the hot gas, the immensely powerful and dynamic magnetic fields threading through it, and the behavior of high-energy particles all at once, across scales from the pulsar's surface to the nebula's faint outer edge. It is a problem of almost unimaginable complexity. Our most advanced supercomputers, running for months, can produce stunning visualizations that capture broad strokes, the overall torus shape, the general outflow. But they consistently fail to replicate the intricate details that make the crab so uniquely strange. The simulations might show a smooth, glowing cloud, but they struggle to generate the delicate, braided filaments, the sudden, relativistic wisps that dance and fade, or the precise, chaotic pattern of the magnetic field polarization. They cannot yet trigger the spontaneous, giant gamma-ray flares with the correct energy and timing. The spectrum, that plot of brightness across all wavelengths, often has a shape that is just slightly off from the real data, indicating our digital physics is still missing some ingredient. Imagine placing two images side by side. On the left, a real multi-wavelength composite from Hubble, Chandra, and other observatories, bursting with intricate, chaotic detail, luminous knots, and complex textures. On the right, the output of a state-of-the-art supercomputer simulation. It would be beautiful, a glowing, ethereal structure, but it would look simpler, smoother, more idealized. The comparison is a direct visual proof of our incomplete understanding. The Crab Nebula is a richer, more turbulent, and more inventive physical system than our most powerful equations, running on our most powerful machines, can yet dream of. It operates in a regime where approximations break down and where we are still learning the rules of the game. Every strange feature we have discussed is a clue, a piece of data waiting to be integrated into a future, more complete theory. For now, the real object remains the ultimate benchmark, not just for our telescopes, but for the very limits of our computational imagination. The final strange phenomenon is not about what the crab is, but what it will become. Phenomenon 25 is the long-term fate of the nebula, a future written by the very mysteries we are trying to solve today. The pulsar at its heart is not immortal. Its furious spin is its fuel, and it is slowly, inevitably bleeding that energy away, powering the wind and the radiation that make the nebula shine. Over hundreds of thousands of years, this spin will decay. The pulsar's heartbeat will grow sluggish, its wind will weaken from a hurricane to a breeze, and finally it will fall silent. When that happens, the brilliant glow of the nebula will begin to fade. The synchrotron light, fed by the pulsar's relentless particle acceleration, will dim first, like a city whose power plant has been shut down. The X-ray torus will dissolve, the gamma-ray halo will vanish. The optical filaments, those beautiful, braided threads of glowing gas, will cool and grow dark, no longer energized by the shocks and turbulence from within. But the story does not end there. The vast cloud of enriched material, the stellar debris laced with carbon, oxygen, silicon, and iron forged in the star's heart and its explosion, will continue its outward journey. It will coast on its momentum, a ghostly shell expanding into the galaxy. This is where the nebula's final act begins, its integration into the galactic ecology. The expanding shell will plow into the interstellar medium, that thin gas between the stars. Over millennia, the two will mix. The shock front will heat the surrounding hydrogen, and the heavier elements from the supernova will be scattered like cosmic fertilizer into the void. This chemical enrichment is the true legacy of stars like the Crab's progenitor. Those atoms of oxygen and iron, once trapped inside a giant, will eventually find their way into vast molecular clouds. There, gravity will pull these clouds together, and new stars will be born from this enriched material. Some of those new stars will form rocky planets, and on those planets, the iron from a supernova that exploded 1 billion years earlier might become part of a mountain, or the oxygen might fill an atmosphere. The strange phenomena we see today are the violent processes that prepare this material for its future. The turbulent magnetic fields that braid the filaments are stirring the pot. The particle acceleration that creates the flares and wisps is ensuring the debris is thoroughly energized and fragmented. Even the faint, asymmetric shell and its interaction with the interstellar medium are setting the stage for how this material will eventually disperse. To visualize this epic journey, picture an artistic sequence spanning hundreds of thousands of years. We begin with the Crab as we know it now, a brilliant, intricate whirlpool of light. Decades flicker by and the wisps dance, the flares ignite and fade, but the overall structure remains. Then, the centuries begin to blur. The central glow softens and shrinks as the pulsar wind weakens. The nebula becomes more diffuse, its colors shifting from brilliant blues and whites to deeper reds as the gas cools. Over tens of thousands of years, the last traces of synchrotron light wink out, leaving only the expanding shell of warm, chemically rich gas, now visible only to infrared eyes. This shell continues to grow, becoming vast and faint, merging with the background of the galaxy. It becomes a gentle ripple in the interstellar sea, a memory in gas and dust. Understanding this life cycle is about more than one beautiful object. It connects the violent death of a star to the birth of everything that might follow. The Crab Nebula is a single, spectacular moment in a grand, billion-year cycle of destruction and creation. Its 25 strange phenomena are the complex, beautiful mechanics of that single moment, a fleeting signature of chaos that will ultimately sow the seeds for futures we can only imagine. The journey through these 25 strange phenomena reveals a single, profound truth. The Crab Nebula is not a static museum piece, a fossilized remnant of an ancient event. It is a dynamic, chaotic, and ceaselessly challenging cosmic entity. Every pulse from its spinning heart, every sudden flare, every wisp moving at half the speed of light, is a real-time experiment in physics pushed to the breaking point. The faint shell, the chemical mismatches, the braided magnetic fields, they are not flaws in a perfect picture. They are the picture itself, a portrait of nature's beautiful, untidy ingenuity. Each mystery we have explored is a window into a realm of extremes, where matter is crushed into impossible densities, where magnetic fields snap with the energy of stars, and where particles are flung across the void with forces we cannot yet name. This object, so familiar from 1,000 astronomical images, remains one of our greatest teachers and our most formidable puzzles. It reminds us that the universe is not a placid clockwork, but a living, breathing, and often violent engine of change. So we turn the question to you after this journey through its heart. What did you find most fascinating? Was it the temperamental pulsar with its off states, the ghostly faintness of its shell, or the sheer violence of those impossible gamma-ray flares? Share your thoughts in the comments below, and the next time you look up at the night sky, find the constellation Taurus. With a simple astronomy app, you can pinpoint the very spot where this cosmic drama is unfolding, a faint smudge of light that contains a universe of mystery. If you enjoyed this deep dive into the universe's greatest puzzles, consider subscribing for more journeys to the edges of our understanding. The cosmos is full of stories waiting to be told.